Okay, I think we are going to go ahead and get started. So my name is David Gottfried. I'm the Deputy Director of the National Nanotechnology Coordinated Infrastructure. I want to welcome you to another installment of the NNCI webinar series, this month focusing on computation efforts. And before I turn it over to my colleague, Azad Naimi, to introduce today's speaker, just a quick note. You can see all of our upcoming events on the NNCI web site, nnci.net. You can view recordings of past webinars on our YouTube channel, and you can get to that if you just Google NNCI YouTube. We should be the first link that pops up. And also to remind everybody that if you want to ask questions, we'll be having questions at the end of the webinar, and just enter them into the Q&A box at the bottom of your Zoom screen, and then we'll read them out for today's speaker. And with that, I will pass it off to my colleague, Azad Naimi, who's Associate Director for Computation for the NNCI.
Thank you very much, David. Today, it's my pleasure to introduce our distinguished speaker, Professor Tony Lowe. He is the Paul Palmberg Professor in the Department of Electrical and Computer Engineering at the University of Minnesota. He's also with the graduate faculty in the Physics Department at the University of Minnesota. His group works on materials and device modeling, focusing on the theory of electronic transport and electromagnetic phenomena at the nanoscale, and the impact of these phenomena on next generation nanoelectronics, spintronics, and plasmonic devices. He has worked in a few experimental groups before joining University of Minnesota, including IBM T.J. Watson Research Center. He was an industry liaison working with various universities under Nanoelectronics Research Initiative, which has had the goal of finding the next electronic switch. He has received many awards, including George Taylor Award for Distinguished Research in 2021, the McKnight Presidential Fellowship in 2019, and the IBM Pat Goldberg Memorial Best Paper Award in 2015. With that, I pass the podium to Professor Lowe.
Thank you. Thank you, Azad, for the kind introduction and for hosting the seminar. So it's my pleasure to give a presentation about some of the recent progress that we made in on the research on spintronics. So the talk that I'm going to focus on today is energy efficient magnetization switching with spin orbit top. And first, I would like to acknowledge the students who have done all the work. And I also want to acknowledge my experimental collaborator, Wang Jianping at University of Minnesota. So the work is primarily supported by C-Spin and Intel, and also part of it by the Smart Center, which is jointly supported by SRC and also DARPA. So with that, let me get started. Okay, so the spin orbit talk was, first, this is one of the first experimental study that demonstrate that you can use the spin current that is produced by Spinhole materials to switch the magnetization of a magnet that is overlaid on top of that Spinhole materials. So what is done in this experiment was the application of an electrical current. And what they observe is that with that application of electrical current, they observe a switching of the magnetization of this nanomagnet. So the origin of this magnetization switching was believed to come from primarily two sources of spin polarization. The first comes from the Spinhole current that could be produced in these strong spin orbit coupled materials. And I'm going to discuss, what exactly and how we think about the Spinhole current. And then the other mechanism comes from what is called the Rashba Edelstein effect. And this, the origin of Rashba Edelstein primarily comes from surface states, or sometimes even bulk states, which has a particular spin texture. And if you go off from equilibrium, then you can get a net spin polarization. So I'm going to focus on these two mechanisms for generating that spin polarization, and how one can, try out different types of materials and to enhance the switching energy efficiency of this device. So by the way, if you have any question, please feel free to interrupt at any point of my presentation. Okay, so what I have here is a slide that try to give a intuitive picture about what is a Spinhole effect. So you might be very familiar with what is called the Magnus Effect, where you can have by exerting a longitudinal force on a spinning ball, you are able to acquire a transverse motion. So the origin of this Magnus Effect is because the spinning ball, the internal spinning degrees of freedom, is interacting with the viscous medium, which then produces some air pressure and causes a transverse force on the ball. And in a similar fashion, in electronic system, the electrons also have their own internal spin degrees of freedom. But if you just have an electron spinning by itself, you wouldn't get any transverse force. But in materials, often we have what is called a spin-orbit coupling. The spin degrees of freedom interact also with the orbital degrees of freedom. So you can think of the orbital degrees of freedom as an orbital motion of the electron, but more on the angular momentum of the electron rather than just the spin. So that interaction between the spin and angular momentum can also produce a transverse force, which then result in the spin moving in the transverse motion, with the application of a longitudinal electric field. So you have the upspin going in the positive transverse direction, and then you have negative spin going in the negative direction. So the Spinhole effect is very sensitive to the symmetry of the materials. So in this few slides, I'm going to give a quick overview about how symmetry dictates the Spinhole effect in the materials. So let's consider a slab of non-magnetic materials, and based on this geometry, we can see that it has the following symmetry. So first, it has this C2z rotation symmetry, meaning that if you rotate by 180 degrees around the z-axis or the x or the y, the materials or the system restore back its original position. And you can also see that the materials also have this mirror plane symmetry along the yz, xz, and xy. But if you apply an electric field on this material, then you're going to break the rotational symmetry, because now you can have a current flow along the x direction. So therefore, if you perform that rotation around the z-axis, you will find that doing that C2z rotation would then transform the current from going in the plus x direction to the minus x, which therefore break the symmetry. And you can also check that the mirror plane symmetry for this system will be broken for the YZ mirror plane, whereas the XZ and the XY, they still preserve this symmetry. So with that in mind, okay, so we have established that with the electric field, we are only left with three symmetry operation. And then we ask the question, okay, what type of current will be allowed by this symmetry? So we can have the first case, which is the charge current. So with the application of electric field, we ask the question whether there could be a transverse charge current. And what you can show is that the symmetry of these the XZ symmetry, which is this mirror XZ plane, it doesn't, it allows this charge current to flow, but then the XY symmetry wouldn't allow this charge current to flow, because if you perform this mirror operation under XY, the charge current would then have to flow in the opposite direction. And similarly for the C2x rotation, you can also show that rotation will also flip the sign of the current. So therefore, this charge current, this transverse charge current is not allowed because of the fact that it can't satisfy all the symmetry operation in this material. And how about the case of a Spinhole current, which is a transverse spin current? So let's look at a case here where you have an electric field going in the X direction, and then you have a spin current going in the Z direction, and we have the spin polarization that is pointing along the X direction. Okay, so we call this type of spin current QZX. Z represent the direction of the spin current flow, and X represent the orientation of the spin. And you can show that, for example, let's look at the XZ. Let's look at this XZ mirror plane. If you take this X spin and then do a mirror reflection around the XZ mirror plane, you're going to find that the spin is going to flip. Okay, that's because spin is a pseudo vector. So one way to think about that mirror operation is think about a spin that is that has this rotation, and with this rotation under this mirror operation is going to go in the counterclockwise direction. So, all right, so sigma Z will not preserve the symmetry, but then sigma XY, okay, which is the mirror plane, which is the XY mirror plane. If you have a spin which is pointing in the X direction, okay, then upon that mirror operation is going to flip the spin. And this is fine with this Spinhole current, because when you do a mirror operation, you flip the direction of the current and you also flip the direction of the spin. So this, okay. So this mirror operation satisfy the symmetry of this Spinhole current. But because of the fact that it doesn't satisfy the other symmetry operation, therefore, this is also not allowed. And if you go through all the other possible spin current, you'll find that this particular component, okay, let's look at what this notation means. The electric field is pointing along X, and the spin current is going in the Z direction, and then the spin orientation is along Y. So in other words, you have this charge current, spin current, and spin orientation all in the orthogonal direction. And what you can check here, what you can show is that this particular spin current respect all these symmetry operation. So therefore, this is allowed spin current in the system. So, which is a reason why in most Spinhole materials, conventional Spinhole materials, especially those with high symmetry, the spin current flow in the direction that we just described. So you have an electric field along X, the spin current go along Z, and the spin orientation going along Y. Okay, and that's a quick introduction about the Spinhole effect. So Rashba Edelstein effect refers to a non-equilibrium spin polarization that arises in materials which has a well-defined spin texture. So this was first discovered in Rashba-like materials, which has the following Fermi surface as shown here. And you can see that for every electron with a given momentum, it has a very well-defined spin momentum locking. So the momentum and the spin orientation are always 90 degrees. So this type of spin texture, where the momentum and the spin are locked, would then implies that if you apply a charge current, and what does a charge current do is that it basically impart a net momentum on the electron. So with that net momentum, it would then also implies a net spin polarization. So another way of visualizing this is that if you apply a current, you're going to shift the Fermi surface, and that shifting of that Fermi surface is then going to result in more occupation of the plus kx states versus the minus kx states. So hence you end up with a net spin polarization that is pointing along y. So this type of spin texture is also commonly seen in, for example, in topological insulator, particularly for the surface states of those materials. And the surface states of the topological insulator have this linear dispersion relation, which can be described by this Dirac cone. And the electron and the spin also have this well-defined spin momentum locking. So one point that we can make also is that, you know, this spin polarization that arises from the Rashba Edelstein is what we call a Fermi surface effect, because it comes from the shift of the Fermi surface. And whereas for the Spinhole effect, we view that as coming from the Fermi sea, because it's a phenomena that comes from the collective contribution of all the electrons deep in the Fermi level. Okay, so when we first look at this spin orbit top, one of the first material that we look at is topological insulator. So in this work, we study the Rashba Edelstein effect. And here what I have is a topological insulator. And we ask the question, what will happen to the, whether we can engineer the Rashba Edelstein effect by going to nano dimension. So we look at, in this case, it's a bismuth selenide, and we look at a nano wire of this bismuth selenide. So what you see here is a cross section of that nano wire. And what you see on the right is a plot of the band structure shown on the dashed line. So I have the, so the band structure is going to be all the same, but what is different for the top surface and the right surface, as shown in this color plot, are the electron density, the surface local density of states, and also the spin polarization on these two surfaces. So what you can see from this plot is that on these different surfaces, the local density of states and the spin polarization doesn't look exactly the same, and that's because of the different termination of the bonds on these two surfaces. And we also observe that there is a small gap that is open. So in the case of a slab, we should get a Dirac, we should get this linear dispersion as what we shown in the previous slide, the Dirac cone. But because of this quantum confinement, we open a very small gap. And what is interesting is that we see that the surface states no longer reside on the low energy band, on this Dirac band, but it in fact migrate to the higher energy bands. Whereas on the other surface, it still reside on these Dirac bands. And okay, and that's the first observation that we see. And we also observe that the surface states also occupy the higher energy bands rather than just the first band. And if we look at the spin polarization, we observe a very clear what we call the spin momentum locking. So if we look at the spin polarization along the positive k direction, we see that it's negative. But then if we switch the direction of the momentum, we see that the spin polarization also switches sign. And that spin momentum locking is somewhat, it's sort of expected because of time reversal symmetry. This material is non-magnetic. So therefore, if you switch, if you go from plus k to minus k, and you go, the upspin should go from upspin to downspin. Okay, that's just a simple consequence of our time reversal symmetry. So with that, we know that, okay, since the spin momentum locking survive, we should also expect to see a Rashba Edelstein effect in this nanostructured material. So that's the first important conclusion, is that even after going from a slab to a nanowire, that quantum confinement still preserve that spin momentum locking, and therefore we should still expect a Rashba Edelstein effect. So here is a study of the density of states and the local density of states, and also, in this case is the integrated density of states and the spin polarization on the surface. But then for the case of, in this case, we want to analyze, the case of a quantum dot. So because of the fact that in this quantum dot, you don't have periodicity in any dimension, so therefore, we can't plot the band structure. But by looking at the density of states, especially looking at the Van Hoff singularity, we are able to identify the energy levels of those quantum dots. So what we see as we go from a slab to a wire to a dot is a more prominent local density of states of Van Hoff singularity in the density of state spectrum. And we also see a similar spin, resonance in corresponding to this Van Hoff singularity. So we can, doing a transport study, in this case, we use quantum transport within the Landauer formalism. So we can compute the spin polarization upon the application of a charge current. So basically, this is the Rashba Edelstein effect. And we can plot the ratio of these two, which basically give us a figure of merit of how efficient this material is able to produce spin polarization for a given charge current. And here what you see is a survey of this figure of merit for different carrier density, for different dimensionality. So we have the case of a slab, which is this black curve, followed by the wire, and then followed by the dot. So what we see is that for each of these cases, there is a optimal figure of merit at some carrier density. So that carrier density, of course, can be engineered in the experiment, and we also see that there is a dependence on the size of the size of this quantum dot. So as we decrease the grain size, we see an enhancement in this figure of merit. So this is the experiment done by Wang Jinping group at the University of Minnesota, where they grow this polycrystalline bismuth selenide. And by using, by controlling the temperature and pressure, they are also able to control the size of the grain. So in the experiment, they measured the what we call the Spinhole angle, which is sort of analogous to the figure of merit that I just shown, which is the ratio between the Spinhole current divided by the charge current. And they observe a ratio that is about 10, which is much larger than what one would observe in the case of a TI slab. So this is consistent with the observation that having a nanostructure helps to enhance that figure of merit. And also, they observe this effect at very high doping carrier density. And by doing Hall measurement, they are able to confirm that that density is around the same order of magnitude as what we observe here in the calculation. So this Hall angle of 10 is sort of encouraging, because in the spirit of trying to have low energy switching, what you want is to be able to apply a charge current. But then, for example, you apply a unit of charge current, you want to be able to get, for every electron, you want to be able to, impart multiple ball magneton to the magnet. So a ratio of 10 is implies that you can, be 10 times more efficient than just, injecting a pure spin current, for example, in what you have in the MTJ. Okay, so yeah, and after that, once we know the spin current, then we can also study the torque that is produced by the spin current. And this is done normally within this Landau-Lifshitz-Gilbert equation. So this is a equation that is commonly used by folks studying magnetization dynamics. And you can insert this the torque into this LLG equation, and explore how the magnetization is going to be influenced by the torque. And I'm going to give a very quick, idea about how the spin polarization is going to affect the switching of the magnetization. So let's again use the same coordinate system that we've been using. Okay, so the XY coordinate represent the plane of the materials, and then the Z direction is the outer plane. So in most experiment, what we want is to be able to switch the magnetization from, say, plus Z to minus Z. And let's consider that we are able to produce spin polarization along Y and Z. Okay, and let's look at the type of torque that is produced by these two spin components. So for each of the spin component, you're going to get two types of torque. One is called a damping-like torque, and the other one is a field-like torque. And what I show here is a block sphere representation of the direction of the torque as a function of the magnetization orientation. So for example, if my magnetization is pointing to the North Pole, then my torque is pointing towards me, okay, or rather pointing towards the Y direction. And if my magnetization is pointing in the X direction, then my torque is pointing in the Y direction. So what you see here in this block sphere representation is that the torque is trying to push the magnetization from the minus Y direction to the plus Y direction. So this torque will be helpful if you want to switch an in-plane magnetization from minus Y to plus Y. And then accompanying the Y polarization is also a field-like torque. And what the field-like torque does in this case for the Y component spin is that it causes a precession around the Y axis. So, and if you look at the Z component spin, and here in this case, what you have is a torque that switches a magnetization from plus Z to minus Z. So this will be, what you want if you want to switch the perpendicular magnetization. And of course, accompanying this damping-like torque is also a field-like torque that has a precession around the Z axis. So, all right, so then let's recall the device geometry that we have. We have a current that is flowing, say, along X, a charge current flowing along X, and then which then produce a spin current going along Z. But then remember that we discussed the right-hand rule that the spin orientation must be orthogonal to the spin current and the charge current, which means that the spin orientation must be pointing in the Y direction. So if that's the case, all right, if the spin orientation is pointing along Y, then it means that, we will not be able to very efficiently switch a perpendicular magnetization. And, all right, and therefore, we are sort of, posed with this problem. What should we do to the Spinhole materials in order to come up with a spin polarization that is pointing in the Z direction? And that led me to the next work. And before I go into the motivation of the next work, let's review briefly the formalism that we're going to use to calculate the Spinhole current. So for the Rashba Edelstein, one can use, for example, as what we described just now, the Landauer approach, or more, and some folks here, or what we call the non-equilibrium green function, as what some folks here are doing. But in the Spinhole case, because it's coming from a Fermi C, contribution, the Landauer approach doesn't allow us to, capture this. It's primarily a Fermi surface, phenomena for the Rashba Edelstein. So for the Spinhole, what we need is a formalism that allows us to capture both the Fermi surface and the Fermi C. And what is most commonly done here is using what is called a Kubo formula. And here what I have is the expression that one would use to compute the Fermi surface contribution and the Fermi C contribution. So let's, briefly go through some of the quantities here that one will need to compute these two numbers. So the first is we need the wave function of the block states. And this is the spin operator and the velocity operator, which one can define once you have the Hamiltonian. And you also need the eigen energy. And this basically, if you have the Hamiltonian, you are able to compute all these quantities. And once you obtain once you obtain this quantity, sometimes we want to also include a broadening to mimic the disorder in the system. And in the Fermi C, okay, it's a similar, somewhat similar expression, except in this case, if you notice the summation here, we are summing over bands which are not the same, which have different indices. And the reason is because the Fermi C effect is coming from an interband contribution. So if you look at the terms over here, we are basically computing matrix element coming from different bands. Okay, so once you compute the spin polarization, the spin density, the non-equilibrium spin density from this Cobalt formula, then you are able to compute the non-equilibrium spin torque. And all right, so there are different parameters that sometimes we often use to compare the experiment. So for example, in the experiment, there is a standard way to measure the damping light torque and also the Spinhole angle. So this Spinhole angle is the ratio between the spin current and the Spinhole current and the charge current. And then there is also this ratio which we denote as beta, which basically is the ratio between the field light and the damping light torque. Okay, and from this ratio, one can also obtain the field light torque. Okay, so so sometimes we like to compare these quantities with the experiment. Okay, so let's look at the first proposal that we have to try to overcome the limitation of trying to acquire Z polarization so that we can switch perpendicular magnetization. So one of the first idea that we look at is by using transition metal dichalcogenides. And these are 2D semiconductors, which has a rather large spin-orbit coupling. And they also have, they have a Brillouin zone that is very analogous to graphene, which has this hexagonal Brillouin zone, and it has the, for the monolayer case, the conduction and the valence band are direct band gap, and they also reside at the kappa and the kappa prime point. So what is interesting about this material is that for the valence band, the kappa valley and the kappa prime valley, they have different spin polarization. So in one valley, the spin is pointing up, and in the other valley, the spin is pointing down. And the nice thing about this spin texture is that all the spin are pointing in the Z direction, which is basically what we are looking for in order to switch a perpendicular magnetization. So we decided to look at this material and study the efficiency of that spin injection into the cobalt ion or other types of magnetic materials, and also to compute what is the figure of merit for these materials. So another quality of this material, which is also of this transition metal dichalcogenide, is the long spin valley diffusion length of order of 1 micron, which allow the spin to diffuse much longer distance compared to a lot of the Spinhole materials. And also the Spinhole angle has been shown to be larger than 1. So this all suggests, pointing to the direction that this might be a good materials for Spinhole devices. So we look at the device structure as follows. So let's look at a transition metal dichalcogenide where we pattern into this cross shape. And what we will do is to apply a charge current in this vertical leg. and this charge current is then going to produce a Spinhole current, or in this case, the valley and the spin are locked. So sometimes we call that Spinhole current, sometimes we call that valley Hall current. And this Spinhole current will then propagate in the horizontal leg towards this magnet, and one would then be able to inject this spin polarization, this non-equilibrium spin polarization into the cobalt ion. And the question that we want to answer is what is the torque efficiency in this material? So we begin by first solving the transport problem for this crossbar geometry, and this is done by using a drift diffusion model, and we basically set up a drift diffusion equation, and then we solve the this transport problem. And what you see here is the plot of the valley polarization on this horizontal leg as a function of the Spinhole, as a function of this valley Hall angle or the Spinhole angle. And what we observe is that there is an optimal Hall angle which gives rise to the maximum valley polarization, and that occurs around 1. And in fact, that is a result that you can also show analytically for this crossbar geometry. And in this case, we look at a crossbar where the dimension is smaller than the spin diffusion length. Okay, that's because we want the spin to be able to effectively diffuse to the ferromagnet. And here you see a few different curves corresponding to different doping. So the purple curve, which corresponds to the largest spin polarization, is for the case with the smallest doping. And then as you start to increase the doping, you see that the effect becomes weaker and weaker. And this is sort of, you can understand this by, if you look at the 2 bands, okay, so this Fermi level is measured with respect to the band age of the material. So when you are closer to the band age, it's much easier to deplete, one valley over the other valley. So if you are able to deplete the electron in the other valley completely, then you get 100% spin polarization. So that's basically the reason why for low doping is much easier to to deplete the one of the valley. And this delta U, okay, this valley polarization is of course related to this delta U, which is related to the difference in the Fermi level of the 2 valleys. So in equilibrium, the Fermi level will be the same, but then once you apply a charge current and produce a valley current, then you will get a non-equilibrium difference between this Fermi level in the 2 valleys. Okay, so in order to study the injection of the spin into the cobalt ion, the first thing we need to do is to look at the band structure. And what I have here is the band structure of this TMD and the band structure of the cobalt ion. So in the calculation, what we have is the equilibrium Fermi level is somewhere around here, which is very close to the valence band age. And the color here, the blue and the red color, denotes the upspin and the downspin polarization. So you can see that the 2 valleys have opposite spin. And this is the Fermi surface of this TMD, and you can see that indeed, for the kappa and kappa prime valley, they have opposite spin. So here is the band structure of the cobalt ion. We see that in the Fermi surface of this cobalt ion is very different compared to the TMD, and you can also observe that the majority and minority spin doesn't coincide with the 2 valleys, and the matching between the spin states would therefore be very sensitive to the relative orientation between the TMD and the cobalt ion, and that will be something that we will look at in the next few slides. So the first thing that we calculate is what we call the torque efficiency. So what you see here is the plot of the ratio of the spin spin torque divided by the charge current that you apply. Okay, so we apply a certain amount of charge current, which then produce a certain amount of spin torque. Okay, and what we have here is that ratio. And we observe that that ratio enhances as we decrease the Fermi level, the doping of the materials. And that is, that makes sense because if we are able to reduce the doping, we are able to have produce a higher valley polarization or spin polarization with a smaller amount of current, which is why there is this enhancement of this performance with the doping. But this number 0.1 is also what you get for a spin transfer torque device based on MTJ. So we suggest that this configuration, even though it can be made more efficient by going to lower doping, and also you can also make it more efficient by increasing the Hall angle closer to 1. But the margin of improvement is not that impressive. Maybe you will get a few times an enhancement, but not an order of magnitude. But in any case, that is one of the first conclusion that we arrive at. And then we begin to look at possible way to enhance that performance. So we look at different types of magnetic materials because we see that the matching between the spin states is very sensitive to the band structure. So we also look at other magnetic materials like iron. And we observe that indeed for the case of iron, you get an enhancement compared to the case of cobalt iron. Okay. And the performance is also sensitive to the orientation between the TMD and the magnetic layer because of the matching between the states, the spin states. And here what you see is the figure of merit as a function of this orientation angle. Okay. So, all right, so now coming to the last part of the presentation. So we begin to look at other ways where we can produce that Z polarization. And we begin by looking at materials. In this case, we look at 2D materials. This is a tungsten ditelluride, and this is a material this is a 2D material which has only one mirror plane. Okay, so if you look at the atomic structure, you can see that this is the only mirror plane. So if you perform the same symmetry analysis, what you find is that in this case, this ZZ component is allowed. In other words, you can have a spin current going along Z with a spin component pointing in the Z direction. Okay, and recently there has been some experiment that performed this spin orbit torque on this tungsten ditelluride, and indeed they have also observed this component. So all right, okay, to summarize, the idea is to go from these high symmetry materials to a low symmetry materials. And the benefit of going to these low symmetry materials is that you can also get a spin current that is collinear with the spin orientation. So this is the component that you want. And this is the component that allows you to switch a perpendicular magnetization. Okay, so then we ask the question, what if we go to a material that doesn't have any mirror plane symmetry? And maybe, one can benefit from, the low symmetry materials and get, and open up, different possibility of the spin current. So all right, so this leads us to this last work where we study this Spinhole effect in graphene on TMD. Okay, and we are looking at a system where we are looking at a twisted graphene on TMD, and we are looking at a system where this twist, all right, is assumed to be homogeneous. So this twist misorientation is assumed to be macroscopic. Okay, which people has already shown that you can make twisted 2D materials over hundreds of micron. Okay, so here is a plot of the band structure of graphene on TMD. So because of the large spin orbit coupling of the TMD, it results in a proximal SOC on the graphene. So the band structure of graphene would then be modified from this linear dispersion to this to this spin splitted dispersion. So here the energy scale here is much smaller, is in milli electron volt. So we are talking about effects that are probably only visible at low temperature, but this is sort of a study where we want to understand the more of the fundamental physics. So here what I have is first you have the opening of a gap because of the breaking of the sublattice symmetry, which we're going to show in the next few slides. And also you see that the spin states are splitted. Okay, the up and the down spin now have a very small gap. And one can develop an effective Hamiltonian to describe the graphene. So the pristine graphene is described by this Dirac Hamiltonian, but because of the registration of the AB sublattice of graphene with the different atoms of the TMD, one can acquire a net sublattice symmetry breaking, and this is described by this term. And then you also have a broken inversion symmetry with dipole, which give you Rashba-like term, and also a very Z-man term which comes from the broken sublattice symmetry in the presence of time reversal symmetry. So this is a Hamiltonian that has been developed in these two papers to describe twisted graphene on TMD. So here are a summary of the size of those parameters for different systems that has been studied in literature. Okay, and typically that effect, as I mentioned, is typically very small, of order of milli electron volt. So first, let's look at, say, two particular angle, a 0 degrees case and a 30 degrees case. We see that in these two cases, there is a line of symmetry. Okay, but then if you go to other angles apart from 0 and 30 degrees, there is no mirror, symmetry in those systems. So here is a plot of the parameters, the various parameters as a function of twist angle, and you can, all right, we can see that 0 degrees, these two parameters are 0 because of the symmetry in the system, but then in other angle, they are all finite. So there has been a couple of experiments on this twisted graphene on TMD, and the experiment observed both Spinhole effect and Rashba Edelstein effect. So they are basically a group of paper that observe a larger Spinhole effect, and there's a group of paper that observe a larger Rashba Edelstein effect. So what we want to study in this work is to look at both the Spinhole effect and the Rashba Edelstein, and try to understand what might be responsible for the crossover between these two mechanisms, and also the role of twist angle. So how do we approach the modeling? The first thing that we do is by looking at the band structure of this bilayer system. So we have a graphene on TMD, and we look at different angles. And the first thing that we have to calculate is the band structure using DFT. But then to compute the band structure, we have to make sure that we have a supercell that is, we first have to define a supercell. And to define a supercell, we have to force the two materials to be commensurate, and that will then incur some strain because the lattice constant of the two materials in general are not the same. But then if you, because of that, it's not easy to find, supercell where they are exactly commensurate. So to make it commensurate, you have to strain one of the materials in order to force it to make a supercell. And these are the few angles that we are able to find where the two materials are able to be commensurate, where the strain is less than 2%. So one can also construct a supercell of other angle, but then the strain will be quite large. So these are the 8 configurations that we are able to identify where the strain is less than 2%. So the first thing that we do is to do a DFT calculation of this material. And once we compute the band structure, then we are able to feed the band structure to this effective Hamiltonian that we have over here. And once we have this effective Hamiltonian, that will then allow us to do the spin transport calculation. So first, before we look at the transport, it's very instructive to first look at the spin texture. So if we look at this, what I have here is, let's just focus on the spin texture and let's ignore the orbital texture for now. Okay, all right. So for the spin texture, you see that the spin has this locking with the momentum, very much, similar to what we see in the Rashba splitted bands. But an interesting thing that we observe here is that the spin is not perfectly locked at 90 degrees. There is this canting of the spin away from 90 degrees. And that is something interesting. And what we're going to show is that it's going to produce some Rashba Edelstein effect that is unconventional because of this canting of the spin. Okay, and the orbital angular momentum is basically in the case, the orbital here refers to the px and the py orbital. So in the case of graphene, we know that the graphene is, in the case of pristine graphene, is described only by the pz orbital. But then in this case, because of the twisted, because of this bilayer structure with TMD, now you also have a finite px and py orbital content, and that px and py orbital can also, have a orbital texture, and we see a very strong, similarity between the orbital texture and the spin texture. And I'm not going to go too much into this, but basically the origin of that spin texture that we see here, is in some way can be traced back to the orbital texture. So the formalism is very similar to what I showed in the previous slide. You have two contributions, one coming from the surface contribution, one coming from the Fermi C, and this is what we call the Rashba Edelstein effect, and this is what we call the Spinhole effect. So, so now we have the Hamiltonian, we are able to compute these two quantities. So what you see here is the plot of the Spinhole effect, the Spinhole current, but here I normalize it to the charge current. So this is basically the Spinhole current divided by the charge current. And here is the Spinhole density. This is the Rashba Edelstein non-equilibrium spin density divided by the charge current. And we normalize it to so that these two quantities have the same unit. So what you see here is the Spinhole effect. In this case, is a spin current going in the z direction that is carrying a spin that is a spin current that's going in the transverse direction that is carrying a spin in the z direction. And here what you have is the Rashba Edelstein effect, where you have a spin orientation along y and along x. So if you look at basically both the Spinhole and the Rashba Edelstein, you basically have all spin component, both the x, y, and the z. Okay, and all right, and we see that most of the contribution are most prominent when you are closer to this neutrality point, but then the effects start to decay as you go away from the neutrality point. Okay, I'm going to skip this one in interest of time. Okay, and here is the plot of the Spinhole angle and the Rashba Edelstein angle as a function of different twist angle. All right, we see definitely a very strong dependence of these two phenomena as a function of angle, and the maximum effect occurs at around 30 degrees. Okay. So in summary, we look at the Spinhole effect and the Rashba Edelstein effect in these graphene and TMD twisted materials. And here, what we are studying here is looking at how disorder, all right, the broadening. In this case, we use a very crude way of modeling the disorder just by adding a broadening term. And of course, this is not this is not accurate, because most of the time if you do it in this manner, then it's not going to preserve all right, it doesn't it doesn't preserve the the net current that's coming into the what we call these disorder probes. So but then in any case, it gives us a rough idea of what is happening when we have disorder. So what I have here is we go from low disorder limit to high disorder limit, and what we have here is is a plot of the ratio between the Spinhole effect and the Rashba Edelstein effect. So when you see a red color, it means that the Spinhole effect is dominant. If you see a blue color, it means that the Rashba Edelstein effect is dominant. So what this is telling us is that when the disorder is very small, the Rashba Edelstein is dominant, but then when the disorder is large, the Spinhole effect is dominant. And one can understand this quite intuitively, because the Rashba Edelstein, remember, is a Fermi surface effect. So if this is a Fermi surface effect, then it should be most prominent when the temperature is low, and also when the disorder is very small, which is what we observe here. But then in the Spinhole effect is a Fermi C effect, so it's not so sensitive to the disorder, which is why it survives at very large disorder or very large temperature. So in summary, we look at a Spinhole effect in different material system, and we look at two particular system. One is the TMD, and we discuss how Valley Hall effect can result in a spin torque that you can switch a magnet, and that that Spinhole effect is enabled because of the spin valley locking. And then we also look at twisted graphene on TMD. And in this case, we show that the Spinhole effect comes from the underlying origin comes from the orbital Hall. And and there are probably other mechanisms that one can explore, and we are merely at this point just scratching the surface. But this is a field that is right now emerging, and also a lot of experiments, and so we are definitely continuing looking into this effect in different material systems. So with that, I will stop my presentation, and I will pass over to Azad, and I'll be happy to answer any question.
Thank you very much, Tony. This was very interesting. So let's see. Okay, we have a couple of questions. So can you clarify by some symmetry argument what 30 or to 60 degrees should look like? Will the sign of spin orbit coupling imprinted on graphene change sign, or is it symmetric around 0 to 30 degree and 30 to 60 degree?
Yeah, thank you for the question. Yep. So I think I missed that. I didn't. I didn't mention that. So so the 60 degrees will be the same as 0 degrees. The 60 degrees will be the same because in this if you rotate by if you take the system and you rotate by 60 degrees, is the same as 0 degrees. And you can sort of see, because the graphene here, if you take this as a center, every 60 degrees, you get back the same carbon atoms. Is that okay?
Yes,
so
thank you.
Basically, from 30 to 60, you basically can think of this curve, but then reflect this curve. So do a mirror reflection of this curve, and then the 0 degrees will be the same as 60 degrees.
And yeah, go ahead.
And also there is and you also mentioned the spin orbit coupling, right? So let me talk about that. So as for the spin orbit coupling, for the 60 degrees and the 0 degrees and also the 30 degrees, they all have a spin texture that looks, you know, very much like a Rashba spin texture. So the spin and the momentum are, you know, locked at 90 degrees. But for other angle, you see this canting. So that has something to do with the fact that the mirror symmetry has been broken. So if you look at 0 and 30 degrees, it has this mirror plane symmetry. But then if you go to other angle, there's no more mirror symmetry. So because of the absence of that mirror symmetry, now this type of spin is allowed. Otherwise, it's forbidden. And one way to understand this is if you have a mirror plane, okay, if you have a spin that is rotating, let's say if I have a spin that is rotating in this manner, if I have a mirror operation, then that spin is going to flip. So therefore, the spin cannot have a spin orientation that is along the mirror axis. So if you don't have any mirror plane and any mirror of symmetry, then you basically can have any type of spin orientation.
Okay, one more question. When you select a unit cell with strain to make it commensurate, do you think in reality the system will be strained in order to lock into large Moir lattice, or is it energetically favorable to do so? What does this look like?
That's right. That's a very good question. My honest answer is that probably not. So in this case, I have a 2% strain, and that 2% strain is pretty. So basically, I think maybe one way to put it is that the energy that you incur by straining it by 2% is much larger than the sliding energy. So in that case, then you will expect that the graphene will then prefer the graphene or the TMD would then prefer to slide in order to accommodate a different Moiré lattice, a different configuration. So my answer is that this strain here, in reality, in experiment, you probably will not see that large a strain. Maybe I don't know the exact number, but maybe for this small amount of strain, it might be possible. You might be able to you might be able to lock the graphene onto the TMD. Yeah, because the strain is small, so it doesn't incur. It might be sufficiently lower than the sliding energy, but in most cases, I think I think in the experiment the strain will be much lower. But then we have to, at least in terms of calculation, we do have to incur some strain. Otherwise, another option that we have to, another way out of this is that we choose a much larger unit cell, but that would make it very numerically expensive. So then the justification here is that we feel that we are probably in the limit where that strain doesn't really change too much the energy spectrum that that we are interested in the transport calculation. Yeah, but that is definitely a very good question. So it's always a compromise between accuracy and computational limitation.
So one other question: could you briefly discuss how would your results extend from monolayer graphene to AB Bernal bilayer graphene?
So yeah, that's a very good question. In terms of the calculation, we can pretty much repeat the same calculation for Bernal stack bilayer. And if I have to anticipate what might happen, I would guess that first, this proximity effect is really, is quite weak. So if you have a second layer, a bilayer, most of the SOC will be imprinted only on the first layer. Mm-hmm. And I would expect that the second layer, the proximity effect will be, almost negligible. So I'm not too sure if there is any advantage to go to bilayer. Maybe there could be some different symmetry in the bilayer, or maybe the band dispersion is different, and there could be some difference in terms of the performance. But yeah, but at least from the point of view of proximity SOC, the second layer will not be able to benefit much.
Right. So I don't see any more questions, and for the sake of time, and we really appreciate this presentation. It was very clear and insightful, and it was very impressive the fact that experiments validated the predictions in many cases. So great job. Thank you so much. If there are more questions, perhaps the attendees can directly email you and ask. And the video will be posted online on NNCI website and on YouTube. Thank you very much.
Thank you, everyone.
David, is there any final announcements?
No, just want to thank Tony, and thank you, Azad, and thank our attendees for joining, and we'll see you at the next NNCI webinar.
Yes. Thank you, everyone.
Thank you.
Thank you, Tony. Bye.
Bye-bye.